Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to this continued lecture on this particular topic on mass spectrometry. In the previous class, I have been talking about the isotopic pattern, how it can be helping the process, even the way that the reaction goes, etc. Let us look at the spectra, for example, how we understand the spectra for coordination complexes. So here is, please have you look at this particular slide. And this slide has three mass spectra of the three compounds. One of them is in the iron compound, other is the cobalt, other is the nickel. Three with the similar kind of ligands that the corresponding complexes are shown over there for the iron, for the cobalt, for the nickel. Now, if you look at the spectrum, the labeling is already given over there, and this is the M, as I said earlier, is used for the molecule, your complex, whatever it is. So that is the M with one proton being added, so MH plus. You also see in this particular thing labeled as M plus H minus 2Fe minus 4Cl. The chlorides last and the iron last. So that means here there is some fragmentation is taking place, and without fragmentation also you have smaller species, with fragmentation is a greater species. In the fragmentation, what you are doing? You are losing this Fe with the Cl2. So 2Fe, so FeCl2, another FeCl2. So those two. So that will become 2 iron, 4 Cl, and that is what is lost. So for the whole complex of this is the one around 535 or something like that, you have a mass, and this is jumped to that which is 290, around that. So what is happening in that? You have a loss of the iron chloride unit, one iron chloride unit, another iron chloride unit. So essentially you get your ligand basically into that. Very much of the, if there is some other things are not there. Similarly, if you look at the cobalt complex, again you have M plus H, that is the original complex plus proton with 1 plus. So that means nothing is lost here. But if you look at this particular peak here, this is minus 2CO minus 4Cl. That means this COCl2 and the COCl2 here is lost, just like for the iron. And similarly, if we look at the nickel case, again same thing, M plus H plus and M plus H minus 2 nickel 4 chloride, and these are. So these are all very similar complexes. One is made with the iron, one is made with the copper, cobalt, one is made with the nickel. And now if you look at this and expand, you will find the isotopic peak, distribution, and you can say this particular thing is coming from the nickel only, this is coming from cobalt only, this is coming from iron, and there is no way that you get confused between them if you look at the isotopic peak pattern of each of these. And that is not shown here, because the idea of this particular thing is just to show the fragmentation aspect through this example. Okay, let us look at another example here. This is again with some level of fragmentation. When you fragment the metal having a ligand, suppose if it fragments to metal and the ligand, then maybe two of the metals may combine with a ligand, one metal may combine with another ligand, or two ligands, or Ml may be combining with any of these things. So all these kinds of species are possible in that. So you have the metal part, you have the ligand part, they can combine with the Ml, either you can add one more metal ion or you can add one more ligand to that. So you get a different kinds of species are possible. On the left side, you have the three spectra labeled as A, B and C. Okay. So the A is from the cobalt complex, B is from the nickel, C is from the copper complex. What is the ligand? Ligand is this one, this particular thing, which is diethiocarbamate. NN diethyl dithiocarbamate. This ligand is same across all the things, across all these compounds. So please again have a look at the spectra, because I am showing different features of this. Now, if you look at the spectrum, there are some small peaks are there, something around at 504, 387 and 297. A very large peak is also there, which is at 355. Now, if you look at this 355, which is a major intensity, major current coming from that particular ion, is nothing but the cobalt with the 2 ligands. L2 means 2 ligands. So, this is one ligand of dithiocarbamate, this is another ligand of the dithiocarbamate, this is cobalt 3. So, this whole thing is the positively charged pieces, because the dithiocarbamate is 1 minus. So, 2 such, 2 minus, cobalt is 3 plus, and this 2 minus. So, therefore, you have 1 plus, and that is the major. But you also see few other peaks, for example, where only the 2 ligands together join together through some with a proton in between, and so there is a kind of a dimer of the ligand, and you can see that here. You can also see your COL2, your cobalt L2 is the complex, will add with another L and will give COL3, but very small in quantity. You can see the intensity is so small. So, L3 with the H, and this becomes the plus. So, this kind of a species. So, you can have the breakup, and then any of these components can join with the other ones in the gas phase, and they may be detected as well. And the intensities are very minute, a little bit considerable, and this is the maximum kind of thing. So, same thing I can explain for you can even sit and look into the one which is the very highest intensity in this nickel complex is NiL2, 2 of the ligands together with 1 proton giving this. Reason is that 1 proton is required because the nickel is 2 plus, the 2 ligands is 1 minus each, it will be neutral, and neutral cannot be detected, and this is detected with 1 proton added. So, just they showed 1 proton here, but it does not matter wherever it is added. That is the one, and the ligand itself is the one which you can see, that is again L2H, the dimer of the ligand, the 2 ligands together, and that is also seen as a greater compared to. So, compared to the cobalt species, the nickel species is not as high in intensity with respect to the free. So, that is the nature of the complex which I was telling about. The currents will be dependent on the nature of the species as well. Then you have another peak with the nickel with the 2 of the L's, and 1 more L is adduct is formed. It may not have been coordinated, adduct is formed. So, it is like equivalent to nickel with the L3 kind of thing. So, L2 plus L. So, L3. So, that is the species you can find. In case of copper, you will not find almost any other things, just find only the main complex. So, the level to which it dissociates depends upon the nature of the complex, its stability, its strength, everything, all of those. So, you have this is the highest stable, as you can say. So, you see only the main complex copper with the 2 ligands, which is found without even 1 high proton, because that is you lose one of the electron from the whole, it becomes a positive charge. So, positive charged species can be. Then if you look at the nickel, yes, you have look at the cobalt, and then the cobalt, the next stability is this one, then the nickel. So, therefore, the copper complex is a greater the complex is with the same kind of ligand, diethyl, dithiocarbamate and all these things. The ratio is also same, 1:2 complex, but the species found are different. Species, the extent of species found are different, not the species found are. So, therefore, it is your ionization the species that are formed in the gaseous phase do depend upon the stability and other parameters of that particular compound. So, I will not explain this feature again and again. Now, I think you should pick up that information. Now, I have 2 other panels in this particular slide. The middle panel, please look at. This is a reaction between a copper 2 salt and the diphenyl thiocarbazone. Diphenyl thiocarbazone is phenyl, phenyl is carbazone. Diphenyl thiocarbazone is taken in 50-50 of water and acetonitrile at pH 4.2. And in this reaction, so you do a reaction, you take a aliquot of that and then look at the mass spectrum, and that is what the mass spectrum is. And in this, what happens is the copper 2 undergoes a redox to the reduction to copper 1 by the acetonitrile, and complex is formed. Okay, so you can see that here the copper one forming with the ligand, two ligands, and ligand is a neutral, therefore copper 1 is 1 plus, therefore the total species is 1 plus. Next highest, our highest is here. So copper with 1L is the highest, which at the 317 mass m by z value, and this is 571. Here the z being 1, m by z is equal to m. So the z is being 1. So this is the copper with 1L, copper with 1L and is the highest intensity, and copper with this somewhat lower in intensity, other things are much lower. So copper, two coppers with one ligand with one nitrate, the one copper with one ligand and one acetonitrile. So these are all you can find. You can find a variety of these species in the reaction mixture when you put into the gas phase of that. So that means you are able to characterize a lot of things into this, whatever is formed in this. Now you look at the right end panel spectrum, which is coming from another reaction, which is the aluminum 3 salt of this reacting with salicylic acid. This is the salicylic acid, that is orthohydroxybenzoic acid, and at the pH maintained is 3.8, and this forms coarse above non-nuclear, also binuclear and mixed kind of ligands. Okay, you can see variety of peaks. The peak which is formed here highest is at the aluminum with one ligand with two nitrates and the negative ion. So therefore these are taken from the negative ion mass spectrum. In the previous case it was a positive ion mass spectrum, here the positive ion mass spectrum. Now this is the one, what is the complex here, and this one is without nitrate, to aluminum with the two ligands. This is aluminum, one ligand, two nitrates, the aluminum with two ligands, this is a complex, and then you also have the two aluminiums with the two ligands and three nitrates, the two aluminiums, three ligands with one nitrate here with certain. So that means in this reaction it also goes through partly in the dinuclear complexes besides the mononuclear complex. The mononuclear complex is 1:2 ratio of between the metal and ligand, 1:1 ratio between the metal and ligand, because there is only one ligand is here, here there are two ligands are there, etc. So entire reaction can be gauged, judged properly by using the mass spectrum. Now you can see it's not just the numbers, you can see the nature of the species and there. So let us move on to some examples where we will look at not only just the coordination compounds, but we can look at some nano species, nano composites, nano clusters, etc. Of this. Okay, I draw your attention to this particular slide. This slide has mass spectra, ESI mass spectra shown for a reaction between the gold salt and this glutathione. Glutathione is a tripeptide, containing one of the residue as a cysteine, and cysteine has a SH group. Therefore, the gold salt that you have used can get reduced to the gold 0 and then form the cluster where the glutathione will cover that one. So this is done at the different ratios. The ratio is gold to these things at 1, 2, 3, etc. And if you look at the corresponding mass spectrum at each of the reaction ratio, so this is at one ratio, this is at another, second ratio, third ratio, etc. So you can see the peaks coming from the 2 minus, 3 minus, 4 minus. So it is a negative ion mass spectrometry here, and this mass spectrum you can call it as a low resolution mass spectrum. Now if you focus on one of these, the highest one is here, highest one is here, highest one is here. So any one of these you can focus and look at the high resolution. The high resolution spectra are shown on the right side here. Now if you see the correspondingly for this is the one, for this is the one, high resolution, etc. So what you can see is that this particular thing is forming the gold with a certain number of m and Sg with a certain number of n. So is shown like the other way. This is the n, this is the m. It's okay. So that is where you have here, you can see gold with the thiolate with this glutathione, and those numbers are seen here. So here you have with the more gold, this is shown as the n and m. So the first number is the gold, second number is the ligand. The ligand is the glutathione, so that you can see. So you have this peak has got 38 golds, 24 glutathiones. Here you have 33 gold and 22, 35 gold and 22, and then here 29 gold and 20 the glutathione groups, 25 and 18, 22, 17, etc., etc. You can see the 10, 10, 10, 11. So these are all dependent upon the ratios that you have. The lower the amount that you have, then you see the lower number of thio groups, and the higher that you would see the higher number of things. So you have this has a higher thio group here, and then lesser and lesser and lesser thiol being added, or glutathione being added. So you can see that using the mass spectrometry you can look at the less resolution and identify the peaks. Then you can pick up one of the peak correspondingly and then go for the high resolution, and that will tell you the composition. So this will tell you the composition. So composition basically you can work out from the mass ratios of that, each mass of the gold, mass of the glutathione, and then you can fix that one. You can also further see the kind of a isotopic peak distributions that you have, and you can calculate the spectrum and overlay, and then you can identify further as well. So you can identify the clusters formed, nanoclusters formed from the kind of a reaction that you have done unambiguously without any error. Let's look at another example for the nanoclusters, or they call it as even nanomolecules, they call it as. Okay, here on the top, please have a look at in this slide. This is the AU 329 minus X AgX SR 84. That means golds are replaced by that many silvers. So that many golds are replaced by that many silvers in this thing. So this is AU 329. This is not with the thiol, this is with between the gold and the silver. And you have your the thiolate is fixed in all these things. So you can keep replacing, replace one gold by one silver, two gold by two silvers, three gold by three silvers, etc. You can, it will change both the pattern as well as the position, because you are changing the mass of the gold by the mass of the silver. So the mass of the gold is 196.97, and the mass of the silver is the 107.87. So the difference is there. So based on the difference that you can make out. Now if it is a overall species is Z, so therefore by Z this difference. So this difference is the 89 and by Z, and that's how you can make out the pattern on this. Now let's say that this reaction is done with a starting with a compound of AU 329 cluster. You start with AU 329 with SR 84, and then you start adding 1 Ag and then adding another Ag, etc. That means you are making -1 AU, one gold is replaced by this. So here another gold is replaced by this. So you get your peaks here. So that's what you're basically analyzing, obtaining from this. Now this is done at a 1 to 0.1 ratio. So the gold cluster to the silver is 1 to 0.1 ratio, as you can see here, and this gives the spectrum with a 2 minus, 3 minus, 4 minus, 5 minus, of which the 4 minus is the highest intensity, and this looks like as if it is like a single peak, but if you see expand it, and you can see beautifully very well, and this you can explain by the corresponding how many silver ions. This position will tell you that, and the difference. The difference is 89 by 4 because the Z is 4 here. That is the kind of pattern. So you can, it's like a signature pattern which you can overlay and explain that very clearly. So you can unambiguously identify, yes, 1 is replaced, 2 are replaced, 3 are replaced, etc. Now this reaction is done for different ratios. Ratios at 1 is to 0.01, 1 is to 0.05, 1 is to 0.1, 1 is to 0.2. These are all shown over here, and here this completely AU 329 cluster without any silver at all, with 2 silvers here. So the position has to shift because it is lower mass, because 2 of the golds are replaced by 2 of the silvers. Obviously the mass is lower. Now here 5 of the golds are replaced by 5 of the silvers. You can see the further shifts, and then here 9 of the golds are replaced by 9 of the silvers, then further goes, and then 26 of the golds are replaced by that. And in each you can see the pattern changes can also be identified from this. So the position exact at where the M by Z coming up and the pattern, these will confirm how many of the gold atoms are replaced by the silver atoms correspondingly. Okay, and this whole thing is done for the 4- charged cluster, because that cluster is the maximum cluster that you find, and that is where. So you can call this as a very high resolution, the high resolution spectrum, and shown over there. So you can exactly work out. I hope there is no confusion in this, and each one by one gold replaced by silver, and that. Look at how exactly they are doing in some other example. Here I have AU's 25 rod. This is to start with, this is the AU25 rod. Kindly look at the slide shown here. The structure is the AU25, the thing, and this can be replaced by one of the gold can be replaced by the silver, or one of the gold can be replaced by copper. You can see that here too. So you can see here the silver replaced, it goes in the apical, the top position of that, and in copper it can go here or it can go into this particular position. Okay, so these are found from other studies also, mass spectral, crystal structure, computation. Together they found the position. Mass spectral will tell you that change only, it will not tell you where it was changed. For the methods like cluster, single crystal structure, as well as the computation will tell you where these are located, either at the apex position or at the side. There are two possible ways of this, and it can happen either of these. And when you are losing a gold from the gold cluster, it always loses from the side, but then it is an internal exchange, etc. That is not a part of this particular course. Here we want to see how this is detecting. Now you see, this is your original, the AU25, and this is the peak, looks like as if it is 1. If you expand, then you can see between the 4150 to 4155, a nice structure can be compared with the calculated isotope peak pattern. Now you replace one of the gold by one of the silver, and you can look at the position is changing as well as the pattern change, and the difference between these two peaks. Pattern means pattern look may not change so much, but the distance between the peaks will also change, because you are replacing one gold by one silver, and then here one gold by one copper, and then correspondingly these ones. So you can use the mass spectral technique to identify these nanoclusters, the changes, etc. I hope that you are able to understand all of these very clearly. Now let us move to another part of it. We have looked at the coordination complexes, we have looked at the nanoclusters. Let us look at the proteins and the proteins, metalloproteins, etc., etc. in this. Okay, here is an example. I again draw your attention to this particular slide, please. And is a protein, it's a anti-angiogenic peptide, is a histidine rich glycoprotein. Those are the things. And this is HRGP330. And this protein is incubated with zinc 2 plus. So zinc 2 plus to the peptide ratios are given here. So that is the 1:1. This is the protein or peptide, you can call it as, with 1:1 zinc, so 1:2 zinc, 1:5 zinc. So you are taking your protein and adding 1 equivalent of zinc, 2 equivalents of zinc, 5 equivalents of zinc, and you have the mass spectra at each. So this is your major protein peak coming over here, and if you expand you will get its isotope peak pattern, but that is not very important. Now once you have the zinc, you have a peak with +1 zinc, the +2 zinc, the original protein, +1 zinc, +2 zinc, etc. Then when you add 1:2, you get more of a +1, almost not much of the protein at all. That means all protein molecules are combined with the zinc ions. Some protein molecules with 1 zinc ion, some large number of protein molecules with 2 zinc ions, very few protein molecules with 3 zinc ions. You can expand each of this, you will get the isotope peak pattern. You can completely fit without any ambiguity. Now you add 5 equivalents and your free protein is not seen. With 1, with 2 very little, with 3 metal ion bound protein, 4 metal ion bound protein, 5 metal ion bound protein, 6 metal ion bound protein. So you have a distribution of the species. So all these can be seen, and how will you work out? One is from the position of this, and other is from the spacing of these ones and the pattern of this. The pattern will change here because the number of zincs are changing and their spacing will also change. So one example is shown here for the experimental and theoretical, how you can make that one. So same thing which I have been explaining for quite some time in this class and a little bit in the previous class as well. Let's look at another very similar kind of thing. There are some proteins called, which are generally intrinsically they are disordered proteins, but when you add some metal ions, those disorder disappears and they become more ordered and they become aggregated as well. This is for the cyanocular protein. This protein with manganese salt 1:5, protein with the cobalt salt with 1:10. So you have this peak with the 6 plus 7 plus etc. and 12 plus 13 plus, here with the manganese, here with the cobalt. Now if you expand, you can find with 1 manganese, 2 manganese, with 1 cobalt, 2 cobalt, you can fully explain these things. So that means the protein as such is also there. The protein with 1 cobalt, this much amount of, the protein with 2 cobalt with this much. If you increase the ratio further, you will find probably higher ones. So, okay, and these cobalt bound or manganese bound ones will show the aggregation because this metal ion binding will make this disordered portion of the protein as an ordered protein, and then with the ordering they make the combination of the aggregation of this. Okay, not only that, you can also do some reaction. Here is a one protein called albumin, and this reaction is the acetylation reaction. So here you see the protein as such without acetylated, non-acetylated. So you will have 12 plus 13 plus 14 plus. From this you can calculate, you will get this protein molecular mass 11,444.6. okay. Now this is treated with a reaction, with the acetylation reaction, and then you look at the protein is found in the monomer, protein found in the dimer also, and these are seen. Now if you expand and find out, you will find these are acetylated by 1 acetyl moiety. This is the original one is 11,944.6, and this is 11,986.9. If you see the difference will be matching with 1 acetyl moiety. 1 acetyl moiety. So that means one of the group got acetylated, where that you have to find from other methods. So even sequential cleavage of the protein, and you can find out as well. Okay, this is another example, in the iron sulfur chemistry. Then you have iron sulfur clusters with the 4 iron 4 sulfur clusters, 2 iron 2 sulfur clusters, 3 iron 4 sulfur clusters. But when you look at their mass spectrum, one can find out what kind of proteins, because the degradation of each of these clusters is not the same. The 4 iron 4 sulfur does not degrade almost at all. The 2 iron 2 sulfur will degrade to a little extent. 3 iron 4 sulfur will degrade to a lot extent. So what is that degradation we can make out? This is the rubridoxine, means only metal with the cysteines. Kindly look at this particular spectrum. So there is nothing, the 3 plus 4 plus 5 plus etc. Now this is your 4 iron 4 sulfur, one of the protein here, and this is the one bottom right, 4 iron 4 sulfur, and the below is one of the amino acid, 14th amino acid, which is D, aspartic acid, is converted into cysteine. So D is the mutant. So the mutant spectrum and the thing will not give any breakup of the sulfide ions. There are sulfide ions are there here. There are 4 iron 4 sulfur. It does not break, is intact. Now you go to the 3 iron 3 sulfur clusters, or 3 iron 4 sulfur cluster. You see, this is the original. This is 1 sulfur loss, 2 sulfur loss, and 3 sulfur loss. All 4 sulfurs are lost. So you can find like that. So this kind of a. So that means by measuring the mass spectrum, you can tell whether this is rubridoxin or with this ferridoxin. In the ferridoxin, 4 iron 4 sulfur clusters, or 2 iron 2 sulfur clusters, or 3 iron 4 sulfur clusters. All these kinds of things can be identified from these. Okay. So, that is you can use it as a technique for this one. So, let me give one last piece of information on this, how one can identify the molecular from this distribution peaks of this. Let us say for example 13 plus, 14 plus, 15 plus, 16 plus, 17 plus, etc. You can identify your molecular mass from that. So, you take two consecutive peaks, which is labeled as here as x1, other one is labeled as x2. So, that is what you are getting x1, x2 is, so peak, so that is m by z for that x1, this m by z for the x2 you will be getting. So, that is the from that values. So, that is x is nothing but m plus z mx by this one. So, if you introduce these ones, you can get this molecular mass, which is this one. You can sit and look into the details of that, nothing difficult. Take two consecutive ones and then you can work out. Do not take the one here and one there, because their value will differ by more than 1. So, only the one difference in the charge that you have to take, any two but two consecutive ones, then you can use this formula, and these are the ones that you have. You can calculate the protein mass in that. Okay. So, in these in the previous class and this class together, we have looked at the mass spectrometry in depth at the electrospray ionization technique, but for the coordination complexes, nanoclusters, nanocomposites kind of things, proteins, metalloproteins, and how to find the molecular weight determining from these. In the next class, we will look at the MALDI technique. Next 1 or 2 classes, we will be looking at the MALDI technique and try to make how can be utilized for such kind of a studies of this. Thank you very much.